Hello, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. We have been talking about the impedance calculation of a bundle conductor. We will today continue with that topic. In fact, we will actually today we will look into that how to calculate the impedance of a three-phase unbalanced network in the presence of any ground wire. So, the diagram or rather the configuration what we are considering is as follows. So, I have got three line, so A dash, B dash, C dash, W dash. Here A dash, B dash, C dash are actually the phase conductors, whereas this W dash is the ground conductor. So we have one local ground, we have one remote ground, we have everything, and then we know, and now this is actually grounded, and of course this is VC, this is VB, and this is VA, this would be VA. Now, so then therefore, now we have already actually looked into that how to do the calculation for this. So we can write down that after we write down the expression of all this voltage involving this conductor D dash, and then after that we will simply eliminate this particular current ID. So after that we can write down this following equation: VA, VB, VC, VW is equal to ZA, ZAB, ZAC, ZAW, and then ZBA, ZBB, ZBC, ZBW, ZCA. IA, IB, IC, W. Please note here in these impedances we have not put any overword, so that means these are not the primitive impedances. These are the impedances we calculate after considering the fictitious D dash conductor and then eliminating the current ID. So we have already done that exercise, so we are not unnecessarily repeating that. So this is actually our second step. So we have started with this. So now here it is very simple. So you see, now here I can say that what are the expressions of impedances. Please note these are not primitive impedances. So impedances ZPQ is actually RP, RA plus RD. Here of course J omega K log DE by DPQ. it is for P is equal to Q, and this is for R D plus J omega K log dE by dPQ P not equal to Q. So, and of course RA, RD and everything we already know, so we have already, and of course here PQR, I can say that PQR A B C W. Now here I have got VW because it is a ground conductor and it is connected to ground directly. So then of course VW is equal to 0. So then if this is 0, so now what we do is that we again partition this matrix like this. We partition this matrix like this, and we define this following vectors, that V A B C is equal to V A V B V C, and we also I A B C is equal to I A I B I C, and we again as usual we say that this is ZA. So this 3 cross 3 matrix, this partition is ZB, this is a 3 cross 1 vector, this partition is ZC, this is an 1 cross 3 vector, and ZWW is ZWW. So from here, and of course I have got this partition, I have got this partition. So I partition these vectors and the matrices. So from here I can write down that VABC is equal to ZA into IABC plus ZB into I omega IW. So we just note down the dimensionality, and of course and then we write down that 0, we write down that the second equation would be ZC into IABC plus Z. So we just note down the, just for the sake of more clarity, so we say that this is 3 cross 1 vector, this is a 3 cross 3 matrix, this is a 3 cross 1 vector, this is a 3 cross 1 vector, and this is 1 cross 1 scalar. So this dimension match, and this is essentially 1 cross 1 scalar, this is in 1 cross 3, and this is 3 cross 1, and both them, and of course both these quantities are scalar quantities. So this is also 1 cross 1, so this is also 1 cross 1, this is also 1 cross 1. So both these quantities are scalar quantity. So from here I can write down, so I have to eliminate IW. So therefore IW is equal to minus 1 by Z. So therefore I can write down that VABC is equal to ZA IABC B, C minus ZB into 1 by ZWW into ZC into IABC. So I can write down it's ZA minus, because this is scalar quantity, I take it outside, ZB ZC into IABC. So I call this matrix as, ZABC. So therefore we have VABC is equal to ZABC into IABC. So let us, so now ZABC is actually ZA minus 1 by ZWW ZB into ZC. ZA is, of course, it is a 3 cross 3 matrix. ZAA, ZAB, ZAC, ZBA, BB, BC, CA, CC minus 1 by ZWW, and ZB is A omega BW CW. So it is ZAW BW CW. So this is ZB, and ZC is WAWBWC. So it is ZWA, ZWB, ZWC, WAWBWC. Okay. So it turns out to be, so therefore ZABC is equal to ZA, ZA, ZAB, ZAC, ZBA, ZA omega, ZWA, ZAW, ZWB, ZAW, ZWC, then ZBW, ZWA, ZBW, ZWB, ZWC, and ZCW. And this is got set. Into 1 by Z. So then therefore, so Z ABC is ZA minus. So I can write down that ZABC is equal to ZA dash, ZAB dash, ZAC dash, ZBA dash, 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 dash. Okay, where Z PQ dash is equal to original ZPQ, for example ZAB, minus say ZPW and ZWQ. So it is ZPW ZWQ by ZWW, right, for P and Q is equal to A, B, C. For example, if I say that what is ZAC dash, so it would be ZAC minus ZAW into ZWC divided by ZWW. Similarly, if I say that what is ZBA dash, so it would be ZBA minus ZBW into ZWA by ZWW. So this expression gives the element of all the, or rather this is, or rather this expression is actually the general expression of all the elements of this final impedance matrix. Now here one thing we need to know, that in the presence of of a ground conductor, the impedances they do get reduced. For example, in the absence of the ground conductor, the impedances were ZPQ, but now in the presence of the ground conductor, the impedance is now ZPQ minus this quantity, and as all these quantities are positive, so then therefore ZPQ minus this quantity would be certainly less than ZPQ. So then therefore in the presence of the ground conductor, the impedances actually reduce. Now let us take an example. We will take the earlier example, that the earlier example was like this. So this was actually the ground conductor, but so far in our calculation we have not considered this, and this is the ground. So we said that this is 45 feet and this is A, then B is C, all this stuff we have said, and this is 15 feet we said, this is 10 feet, this is 10 feet, and the length is as usual 40 mile, and we are not considering any transposition. So no transposition, and we are considering no transposition. Right? We are considering no transposition. Now, if you do remember that in the first example, we have considered this example, and there we have calculated the ZABC matrix, but we did not consider the effect of this ground wire. In this example, we are going to use the, or rather we have to we are going to consider the effect of the ground wire. So then therefore all the other pertaining data are same, so we will just mention the extra data. So the extra data is that Rw is 4 mile per 4.0 omega per mile, and dSw is equal to dWw is equal to 0.001 feet. So that's what we know. So then therefore ZWW would be Rw plus Rd right. So Rw plus Rd. Here of course in this case it would be, instead of saying Rp I should have said Ra, I should have said Rp, where Rp is the resistance of the pth conductor. So this would be A, B, C, Q, because when P is equal to Q, so all are same. So instead of saying Ra, I should have said, we should say actually it is Rp, where Rp is the resistance of the pth conductor, where P varies from A, B, C, W, right? And Rd is of course nothing but the ground conductor, or rather the uh, earth resistance, which we have already defined. So this is the earth resistance. So Rw plus Rd plus j omega k log, then it would be dE by dWw. Rw is we have given 4.0. Rd we already said in the earlier example 0.09528 plus j omega, and j omega k is 0.1213. That also we know that it is 0.1213 into log dE is 2790. That also we have said in the earlier example. This is 0.001, right? So it comes out to be 4.09528 plus j 1.8 omega per mile, right? So then for 40 mile, ZWW would be given by 163.8 plus j 72.0 omega, right? Now we have to find out the other. So we have found out this element. Now we have to find out other elements. For the other elements, we have already calculated these elements ZA, ZAB, ZC. We have to only now calculate this, and this. So for that, we know that what is ZDAW, that is the distance between conductor A and the ground conductor. The distance between conductor A and the ground conductor would be nothing but 10 square plus 15 square root. So that is given by 18.03 feet, right? That is also equal to dCW, because the conductors A and C, they are located symmetrically from each other, and dBW is 15 of course, so it is 15 feet, correct? So then therefore what would be the values of D? So then therefore what would be the values of ZAW? That also of course would be is equal to values of ZCW. That would be equal to RD plus J omega k log dE by dAW. So RD is 0.09528, J is 0.1213, then log 2790 divided by 18.03, right? So that comes out to be 0.9528 plus J 0.612 omega per mile. So this is the impedance per mile. So then therefore for 40 ohm, 40 mile, Z, that turns out to be 3.812 plus J 24. And what about ZBW? That would be RD plus J omega k log dE by dBW. Log so it will come out to be 0.09528 plus J 0.634. So for 40 mile, comes out to be 3.812 plus J so then therefore what is the so these values we have already calculated. So 14.932 plus J 58.376, 3.812 plus J 27.332, 3.812 plus J 23.968, and then 3.812 plus J 24.47. So again, so this is symmetric matrix. Three 0.812 plus J 27.332 and 3.812 plus J 25.363 is 3.812 plus J 968, 3.812 plus J 27.332, then 3.24.47, and then of course we have 3.812 plus j 24.47, then 3.812 plus j 25.363, 3.812 plus j 24.47, and this one would be 3.812. We have calculated it. Sorry, no, it would be 163. Sorry. It will be 163. This value, it will be this value, 163.8 plus j 722.0. So this is the Z matrix. So now we do the partition. So we do the partition. So this 3 cross 3 is ZA, this 3 cross 1 is ZB, this 1 cross 3 is ZC, and this is ZWW. And then if we do this calculation ZABC, so we can find out final ZABC is given by 17.5 plus G 56.107, 6.484 plus J 996, 6.38 plus J 21.698, then 6.484 plus J 24.996, 17.712 plus J 55.972, 6.484 plus J 24.996, 6.38 plus 8, 6.484 plus J 24, 17.5. So this is the final ZABC matrix. So you see, if you compare this ZABC matrix with the original ZABC matrix which we have already derived in the first example without considering the ground conductor, you will find that all the values of this ABC matrix are has actually reduced. So then therefore, the presence of the ground conductor reduces the impedances. So with this example, we today stop here, and then we will continue with the other aspects in the next lecture. Thank you.